Okay, class. This week, for our first quality module, we are going to talk about unit testing, both black box unit testing and white box unit testing. I'm going to go through this relatively quickly because this is supposed to be a review. You should have had black box testing in CST316. So it should be something that I'm reviewing for you. You will have a lab accompanying this that should in JUnit inside of Eclipse. Should be a review as well. So we're going to do black box and white box in the same week, which I know will be busy, but again, should be review. Again, a reminder as well from the context of your project and how the class is conducted that once you review these module materials and do the lab, then you're expected to go write unit tests in the project and track where you do those things. And I'll talk a little bit more about that when I wrap up this module. But now let's start. I'm going to start by doing this first video on black box testing, and then there'll be a separate one for white box testing. Okay. So unit testing checks an individual program unit, a subprogram, object, class, package, module, method, function, whatever you define a unit to be, behaves correctly. So it's a functionally oriented test. It's about behavior and it's about correctness of behavior. Unit testing by itself, we're going to talk more in the next session on validation versus verification. This is really a verification activity. It is a pure testing activity. There is a notion of a distinction between static and dynamic testing. Static testing, testing a unit without executing the unit code. Well, if you're not executing it, that's called static analysis, really, more than static testing. So what we're talking about is dynamic testing, testing unit by executing a program using test data. So that's what we're going to talk about, specifically a dynamic technique. That's black box testing. And we're going to talk about two specific techniques inside of here in this section, equivalence partitioning and boundary value analysis. At the bottom, famous quote, and I don't know that I've ever given a testing lecture at any level, unit testing or any other kind of testing, at least functionally oriented, without quoting Dijkstra. All right, program testing can be used to show the presence of bugs, but never to show their absence. So you can't test something exhaustively and say, because I didn't find anything in testing, therefore there are no defects. In fact, the more defects you find, I mean, we tend to think of there's a cup, and that cup is this full, and if I take some out, it's less full. So if I have a whole bunch of defects and I find some and I take them out, then I have less defects. Well, in one sense that's true, but actually a testing process, if it's finding a number of defects, all that implies is really that you have even more defects probably that you didn't discover. The notion of testing effectiveness is called defect discovery. That is the percentage of defects together with defect yield. The percentage and volume of defects that you find in a given software. And next year, you'll take this notion of discovery, this notion of defect yields, and you'll actually calculate defect density estimates, meaning how many more defects are probably in my code given what I've already found already. That's something that you'll talk about next year. Okay, let's jump into black box testing now. Okay. Black box testing, the purpose, test functional behavior, whatever the module is. It's called black box because you can't see inside the box. Drawback, when you find something in a black box test, a functional defect, you don't know why. Usually you don't know why. There's no causality reason. You can't go to a line of code. As a black box tester, you should even have the source code per se. Now as a developer you will, but someone can functionally test something as a point with some compiled artifact and not understand the cause of the defect, only the conditions under which it happens. So the method, treat the module, classic input-output module, provide it with certain inputs, then it should provide certain outputs. All right. How do you determine what are the inputs? How do you determine what outputs to expect? That's what we're going to talk about. Black box testing is also known as specification-based testing. The test case is designed, selected, and run based on specifications. So that's the requirements part of this diagram, meaning you should have some specification, something that describes what the functional behavior is of that unit. Now again, the level of granularity of a unit that we're talking about here could go up and down the scale. The unit could be an entire module, an entire component, an entire subsystem, or it could be as low level as an individual function. But whatever level it's out, there should be some specification, right? In Java, it may be a method with a Java doc that describes what it's supposed to compute given its inputs, all right? And you're going to design your unit test for that method based on that Java doc, based on the documentation of that method, all right? So use those specifications to derive those test cases. What we're going to talk about next, and this is what we're going for, is you look at the specification of something. So you look at, say, a Java method, and it may be something like public. Oops, that wasn't supposed to go to the next one yet. It may say public int. All right, I guess I shouldn't try and do that. It should say public int, add two, for add two numbers, and take int x and int y. All right. Anyway, say that sounds like a very benign method. Its obvious thing is that it should add the two numbers together, right? However, you got to read the specification. Maybe those ints are not meant to be in base 10, like you're perhaps assuming. Maybe they're in some other base of a number. Maybe it'll throw an exception, or maybe it's only supposed to be meant for positive integers. Maybe could mean any other kind of encoding without reading the specification, so that you understand the semantics of the parameters. That aside, though, if it is what you might expect, two integers, base 10 format, you need to go through and identify what are some of the typical values you're going to try. I mean, I've got two ints I want to add together. What's a typical addition? 10 plus 20. I don't know. 2 plus 4. Even with those, I just mentioned two test cases that were only even numbers. Is there some significance to that? Boundary values. Are there any things at an edge case? We know that integers have a particular range of size. A short integer is typically going to go to, say, about 64K in range of numbers, where a long integer is going to have a much larger range. So do we do addition near the boundary of plus and minus 32K? Is it signed? Is it unsigned? Do we know these things? Are there any special cases associated with it? Maybe not so much with integers, but we'll talk about some special cases with some other mathematical functions. And then, are there any invalid input values? Right? Anything that can be encoded in that, either by itself or in combination, that doesn't make any sense. All right? And do we consider those cases that are expected to test our error handling and robustness, if you will, of how we coded something? Not sure why that pen didn't work there. A naive approach to black box testing does that, right? It says review the documentation for expected output. So, you may have a documentation that's something like benign, like a Fibonacci sequence starts like this. And it talks about, 0, 1, 1, 2, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 15, 5, 89. I imagine you encountered Fibonacci sequences when you were doing your induction proofs and your recursive programming, but if you haven't before, you could tell a Fibonacci sequence is a function where the current result is based on the sum of the two previous results. So you may read that documentation and say, I need to come up with a procedure that looks like this. Ask the user to provide a number from 0 to 11 inclusive. Why 11? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. 7, 8, 9, 10, 11, 12, right? There are 12 values there, so I'm going to do from 0 to 11. That has 12 values. I'll call the fib function on each one of those 12 values, and I'll compare the result value to the corresponding value in the list, meaning I'm going to try and write again. Let's see how this goes. Nope. I'm going to see if this will help. So I'm using a mouse now so I don't write as well. So I'll call fib 0, right? And it should equal 0. Then fib1 should equal 1, and so forth. So I'll map the result to one of the output results in the corresponding list. Is that the best way to do it? Does that validate all Fibonacci numbers and all Fibonacci sequences? Did I consider negative test cases? Did I consider boundary cases? Do I have to exhaustively test all 12 numbers, right? I have to do 12 test cases here. Well, this is a relatively small set, but a Fibonacci sequence, in a mathematical definition perspective, goes on forever, right? So how many of these things do I have to try? This simple procedure we call naive, because you only consider the success case, right? The main happy day case and the use case. You don't have special cases in here. You don't have negative cases. What about negative numbers, and so forth. Second, it's naive because it's kind of brute forcing it and it's testing all the values, right? Do we need to do that? Can we validate that the mathematical function or verify that it's working correctly by only using a subset of these tests so we can be more efficient? In that case, we would do something called partition-based testing, which is a little bit better. Guideline-based testing in and of itself is effective. Yes, it's something you should do. But by just reviewing the documentation for the expected output and designing input, you don't know if you're really covering all the values. All right. Basically, if you just do it based on a set of samples, your test may not be complete. So partition-based testing tries to help you be complete. It also helps you be more efficient by really trying to create test cases that are different, that partition the input space so that you pick out representative values so you can test less but do it with more confidence that you're covering all the interesting cases associated with your input values. All right, so let's talk about two techniques for doing that. And they're related. The first one is equivalence partitioning, an approach to black box testing that divides the input domain of a program into classes of data from which test cases can be derived. All right, we got this thing up here called classes or equivalence classes. You should have heard of equivalence classes, right? You took discrete math. In discrete math, I should have talked about an equivalence class and equivalence set being based on equivalence relations. Your equivalence relations being reflexive, symmetric, and transitive. All right, reflexive. If X is a member of the set, then X is a member of the set, right? Seems fairly obvious. There's actually some relations for which that does not hold. Symmetry. If you define a relation X, R, Y, and very often the tilde here is kind of another way of writing it is, and again, I shouldn't use the pen because it doesn't seem to work. Often we'll write this as X, R, Y for symmetry, and that implies, and I'm very sloppy when I try and draw with the mouse, I know. Implies that if X, if the relation applied to X in this binary relation format includes Y, then it also includes Y or X. So for example, something that's symmetric is equality, right? That's symmetric because if X equals Y, Y equals X, right? But the greater than sign isn't, right? The greater than sign is if X is greater than Y, then Y is not greater than X, right? Y is less than X, so therefore symmetry does not hold, okay? What else? Transitivity. If X R Y and Y R Z, then X R Z, right? That holds for both equals and this non-example, by the way, is not in the equivalence class because it's not symmetric. Equals is because it is reflexive. X is equal to X. It is symmetric because if X equals Y, then Y equals X. It is transitive because if X equals Y and Y equals Z, then X equals Z. So equality defines that relation equality, right? Equal sign is the R here. All right, that R defines an equivalence class because it is an equivalence relation. we're saying that greater than is not, right? Is x greater than x, for example? No, so it's not reflexive. X greater than y, then y is greater than x? No, that's not true either. However, it is transitive, right? If x is greater than y and y is greater than z, then x is greater than z. So for this one, we only have transitivity associated with it. Therefore, it's not an equivalence relation and does not define an equivalence class. Okay, so that's 3 minutes of discrete math, right? That you should have already taken. What does that have to do with black box testing? What does that have to do with equivalence partitioning? How does it help? When you identify an equivalence class on your input data, what you're really saying is the data is expected to produce the same result. All right? Meaning you can pick out, when you have that set and you have a set of values in those in different classes, in different partitions, then you really only need to pick out one representative value. And that typically will verify the correctness of the entire set. So it drastically cuts down on a number of your test cases. All right, we're going to see some examples of that. I know it may not be entirely obvious right now. This is a figure out of your book in Chapter 8, the chapter you're supposed to be reading. Effectively, we are trying to identify different partitions. Notice something about this diagram. This is a set diagram. This is a simplified Venn diagram, if you will. In that Venn diagram, we have a universe of inputs. We are trying to identify partitions, meaning these things are mutually exclusive. They do not overlap in any way, right? They do not intersect. The intersection of these partitions for any pairwise set of these partitions is empty. The range of full possible outputs, some is the outer blue circle. The correct outputs, all right, pointed out here, is the inner circle, which means there are some things for which the input will produce an incorrect output or invalid output. Really shouldn't be given as input, if you will. And then there's different partitions, all right, of those things. In other words, I should get representative different results as well. The part really, we're really concerned about this side, right? The inputs here are going to be represented typically by parameter values, right? It technically can refer to anything that any data that you grab that the correct function of that unit depends on. But very often, from our perspective, from a functional programming perspective, meaning a method on Java, a function in a language like C, it really represents the parameters that we're going to pass into that method. And we want to identify their independence, if you will, and understand what output sets they're supposed to map to. Okay, so let's go to a simple mathematical example. Suppose we have a program, a function, that computes a value of a square root of x minus 1 times x plus 2. What are the equivalence classes here? Well, first one, x is less than or equal to minus 2, gives us some kind of valid response, right? Why? Well, if I'm less than minus 2, then this will be, let's say it's minus 3, then minus 3 minus 1 is minus 4, minus times, or minus 3 plus 2, let's say, and what do we get? We get a minus 1. So we would have a minus 3 minus 1 is a minus 2. We'd have another negative number, 2. I think I said minus 4 before. Actually, that's correct. Doesn't matter. Either way, it's negative. You can tell I'm tired on a Friday afternoon. Either way, with x less than or equal to minus 2, this is going to give us two negative numbers multiplied together as a product. Gives us a positive number. We can compute the square root of the positive number without getting into imaginary numbers. However, if I give something in this range between minus 2 and less than 1, then one component of this or the other is going to end up being negative, and I'll have an invalid one. So this would be an example of a negative test. And then I can have x greater than or equal to 1, and again, both this component and this component will now be positive, and again, I'll get a positive result for the product, in which case I can take the square root, and I'm back to having a valid case. So I identified 3 equivalence classes. I should pick test cases from each equivalence class. So I should pick, minus 3 for the first one, I can pick something as simple as 0 for the second one, and I can pick 4 for the third one. Anything that's representative, all right? So I just, instead of the full range of integers and picking things willy-nilly, I have some rationale to pick representative values in these cases, and I only need 3 test cases, and I have confidence that things will work, all right? Now, what are some of the pros and cons of this? Let's start with the cons. First, lacks causality, right? 2 inputs may expect to produce the same output for entirely different reasons. There's no deterministic way to define these equivalence classes, all right? There's no algorithmic way. It's really done by inspection, all right? There are some research approaches to try and identify proper test cases. There are statistical approaches to this stuff, but in its very simplest form, we looked at this and we kind of had to figure it out. And when you look at any individual function that you're going to do for your lab and your project, you got to kind of sit down and sketch it out. What seems to be work, and make sure that these things define equivalence relations, equivalence classes. Some of the pros. Now, it may be difficult to do it in a deterministic or algorithmic fashion, but often it's also not that hard to kind of figure out intuitively, right? Despite my mental fogginess around negative addition, the fact of the matter is, all that mattered is that both components were negative, and so it's not that hard to find these kinds of things. And when you do that, again, you greatly reduce the number of test cases you run. Without this kind of approach, I probably would sit down and say, I need a whole bunch more test cases because X can be in a range of all kinds of integers. So I'm just going to go start grabbing numbers and plugging them in. Usually this will help you, and we'll see this when we return to the Fibonacci sequence. We'll see how that is. All right. Actually, let's return to Fibonacci now. Back here. I got my scribble on here. But remember, we had these 11 values, or 12 values, I should say. For us to test from 0 to 11 inclusive means I had to do 12 tests, counting from 0, and test that I got each one of these values. That's our guideline-based testing. It didn't consider, kind of the range of negative inputs. It didn't consider how, larger values of a Fibonacci sequence and so forth. So if I went back and tried to define equivalence classes for testing on Fibonacci, what kind of things might I have done? Well, I might have started with edge cases, things like fib of 0 and fib of 1. I might have done the last one, right? Fib of 11. And then I might have picked something representative in the middle, fib of 5, let's say, right? Then alone, because, our equivalence class there might be from fib 2 to fib 10. And I might say, it doesn't matter which one in that class I do. I can do fib 5 because they're all part of the same set. In other words, I expect the computation for those things is the same. There's no special case there. So I don't have to test each one of those exhaustively. I would think that by picking a representative value, I've represented the entire class. So fib 5 actually represents 9 numbers going from fib 2 to fib 10. Now you might say as well that, wait a minute, Dr. Gary, you threw in fib of 0 there and fib of 1 and even fib of 11. How did you do that? Well, intuition even here on our square root example says, yeah, I want to pick a representative value, but I'm a little worried about the boundary cases, the things that come on the border, right? I have a -2 here. I got a -2 here. I'm using less than or equals, less than. I have a 1 here, and I have a 1 here. Is my program, my function, my unit going to execute correctly when I get right around -2, when I get right around 1? And what happens again when we talked about addition? What happens again when I get into really large integer cases, both in the negative and positive direction if I'm dealing with that? What happens when I get around special values like 0? Often can make you kind of paranoid. So you also have this kind of special case intuition about things, and that's kind of what I was doing when I was saying what are the different things we would do for fib. In reality, for fib of 0 is a special case. It's computed differently. Fib of 11 is a special case. It's at the end. You want to make sure it's going to be computed a little differently. So I kind of threw those cases in there on intuition. the process related to equivalent partitioning of identifying those special cases is called boundary value analysis. Black box techniques where test cases are designed to test the boundary of an input domain. All right. So, lots of studies can show, and it probably matches your intuition, that more errors happen at these boundaries, right? I mean, even look at our definition here. We're more likely to get an error at these boundaries because maybe our logic was incorrect. Maybe we're not handling rounding. What if somebody handed us a float and we're rounding incorrect? All kinds of reasons. So these kinds of boundaries are what's called the edge case, the atypical special case that needs to be tested. These kinds of things are typically thrown in with the equivalent sets we come up with through equivalence partitioning. So BVA, boundary value analysis, complements and can be used in conjunction with equivalence partitioning. So for example, right, after using our equivalence partitioning to generate the equivalence classes that we did, those 3 test cases, we may want to add additional test cases. So these are our 3 test cases we came up with on the previous slide. But now what if we throw in some extra ones? We might say, well, yeah, it's enough, x less than or equal to 2, but from a computational perspective, I may be interested in a 32-bit system of the max int. I may be interested in the max positive number as well. So I have the max negative, max positive integers. I might be interested in things around the boundaries. Here I'm only using 1.9, but we can go I'm only using 1 decimal place, but we can go out a whole range of decimal places, perhaps decimal places even beyond our capability of our current floats to handle in precision. And I'd be worried about rounding and truncating and data conversion errors from a float to an int, for example. I may try some reasonably larger values, right? What's special about 100? Nothing other than it's kind of bigger, right? I'm kind of throwing it in, if you will. So in any event, these I could use in this case as the typical values, minus 100 and 100 for each one of these cases. I have a couple in here, the -1 and 0 cases. I have it right on the boundaries, right? So in any event, totaling all these up, I went from 3 cases to 12, right? Now 12 is better than exhaustively testing this square root product computation across all ranges of integers and taking tons of time to do that. I reduced it to a relatively smaller number. Even with the Fibonacci, even throwing in the edge cases of Fib 0, Fib 1, and Fib 11, I threw in 3 more test cases based on my boundary value intuition, if you will. But I still have a total of 4 tests. That's still better than exhaustively testing through all 12, right? I've reduced it by 2/3 just in doing so. All right. So taken together, equivalence partitioning and boundary value analysis can greatly help you. Help you to greatly reduce the number of tests that you do, and still be assured of the same level of correctness as exhaustive testing. Now, threw up this example because the next thing we want to go into is if you consider some of your input data, some of the test cases are derived not based on a single dimension of the data, all right? And that's called a basis. A basis is the application of equivalence partitioning and boundary value analysis to a particular dimension of the data, okay? And so, so what do we mean by dimension? Let's look at this example. We have a homework average function. That function takes an array of floats. What does it do? If you look, it's looping through the array. It's finding the minimum at some point, presuming a max minimum of a high number, 99,999. When it identifies that minimum, it tracks it, so it's going to find a minimum somewhere here in an array, a single minimum, and it's going to total up the array, except for it's basically dropped the lowest grade, right? It's going to take the total, subtract the minimum, and return that new total minus the length of the array minus 1. So this is an average, drop the lowest grade, all right? That's what it computes. So let's think about the different ways we would want to black box test this by examining or considering an array of floats that are passed in, and what are some of the different ways we look at an array of floats. What are the different dimensions of an array of floats, if you will? And I don't mean one-dimensional array. I mean the different ways or ways to examine this data and construct test cases. And it kind of goes back to these Venn diagrams. What are the different ways to partition? All right, may not be clear, so let's talk about what some of these different directions are. The first one is just to consider the array length. So one dimension, one characteristic, one basis by which to partition is by just understanding this is an array, which means it's going to have a different length. When someone calls us, now this isn't Java code, this is more C code, but you can understand the pseudocode. One thing is to say, well, what if somebody passed in a null for the array? Meaning there wasn't actually something there. In this case, we'd bomb, right? There isn't any error checking here. There isn't anything, you're not paranoid at all. So checking using a null array might be a special negative testing case, right? A boundary case. Another case might be to consider an empty array. There's actually nothing in here. It's not null, but there's nothing in here, right? That's going to make the code execute different. Now again, from black box testing perspective, I showed you the code so you'd understand how something's computed. But in reality, what we would know, right? We would know this part. I mean, if we're the developer, we are, but if we are a specification-based tester, I should be able to write the unit test based on the understanding of this functional signature and documentation that says the purpose or the output of this function, this float, is supposed to be the average of this the scores in this array minus the minimum score, right? If you know that, if that's the specification, and you look at this method signature, you don't need any of this stuff, right? You don't need any of it. You're not supposed to have any of it, frankly, when you're black box testing. All right, let me clean this up. Okay. So we're focusing on this, and we're saying, okay, null array, empty array, or an array of one element. What happens when you have an array of one element? What happens when you have an array of 2 or 3 elements? Again, something now representative. What happens when you have lots of elements? What happens when you have scores length of elements and so forth? So realize that you're going to partition array length based on how many things are in there, and roughly it's going to be kind of empty, one, small, large. These are going to be examples of different bases, of different, I should say, equivalence partitioned classes based on the basis of the data considering array length. All right, we haven't taught none of this identification of a test case said anything about what values actually put in the array of scores. Right? There's anything in there about that. It's all about just the length of the array. So now we can go to cases where we start to consider other aspects of the array. Right? One aspect of the array would be to consider where is the minimum score in the array. Right? Is it the small element is first? Right? We put the min right in the very first element. Is it that the smallest element is the very last element? Is it the smallest element is in the middle, right? Somewhere in the middle. These kinds of partitions, which really these should be mutually exclusive again. I should have separated those. These identify different equivalence classes, different partitions, based on just considering where the minimum score is in here. Again, I didn't need to know the code for that. I just needed to look at this, and just by my knowledge of knowing what an array of numbers is, all right, I can now consider, I said, I should explore. I don't know how it computed. I don't know how it, I don't know if it works from the array from back to front, from the middle out, from the front, first element to last element. I don't know the code to be able to write that test. I don't know that this is how it does it, all right? I can look solely at the input domain and say, and know from the specification that I'm looking for the minimum to say a basis for this is where is that minimum score actually reside inside of the array. Okay. Now the next thing right? We're not done. So we consider the length of the array. We consider where that minimum actually is. Another thing we can consider, maybe you thought of this, is, well, what if I got more than one minimum, right? What if I, scored 0 on 2 different things inside of scores, all right? So I can get into the number of minima. I may have one unique minimum. I may have all of them being the same. What if I scored 100% on everything, right? And I may have just a few minima, right? Now, in a correctly written specification, I'd actually be told what to do, right? Because if someone just told me in plain English, calculate the homework average minus the minimum score, it's not actually giving you information about what to do. It's ambiguous, right? We don't like when our requirements are ambiguous. So sometimes this can even help us understand ambiguity in our requirements. Something that's written more precisely, like a single copy of the minima, or the homework average is equal to your score, the average of all your scores after you subtract out the single lowest score, right? We can try and use more precise language. But since we didn't, I'd probably look at that specification and that method's or function signature and say, look, I've got to look and consider cases where, I've got, just the one is the normal case, one minimum. That's kind of what you might expect. I might have 2 minima. I might have all the data being equal, right? And to ensure I still get a correct computational case, it would expose faulty logic. If, for example, there are 2 more or more minima and I get the wrong answer, right? Then somebody's pulling out something based on an algorithm that's not functionally correct according to the specifications. Okay, so that's the notion of different bases. Even in a very simple example, right? We had to consider this different dimensionality of the data, which means now I got to start thinking of a number of different test cases, right, to combine in order to cover all of those different bases. Okay. Okay. Food for thought, and I'd like you to pause the video after I talk about this problem and have you think about the answer before I continue talking about it. I want you to look at the specification, the documentation of these 2 methods, as well as their signatures, and first try and figure out which one's going to require more tests. And is that the same thing as saying which of the 2 is easier to construct black box tests for? Pause the video for a moment. I want you to contemplate those 2 questions, and then let's talk about it. Okay, hopefully you unpaused, you considered that. Which of these 2 methods requires more tests? I didn't go through the exercise of writing out all the test cases. Hopefully that's what you did. But when considering these things, I mean, how do you look at this documentation and this method signature and try and figure things out? Well, you should take out a piece of paper and try and understand what the different cases would be. So the functional specification of the first method is to determine if a string is a palindrome, right? A string that's a palindrome is something that is the same forward and backward. So it may be, for example, my wife's favorite musical group. Not really, but she liked that movie they made a number of years ago. Same forward as backwards. So I'm going to accept a string as an input parameter, and what I'm going to return is a Boolean. And I also have some fundamental error checking built in. I'm a little paranoid. I actually have an exception saying I'll define an exception if the parameter isn't a string, meaning it has white space. I guess string isn't even the right specification. A single word, I guess, is what it should say there. But in any event, I don't want to allow strings that have white spaces. And if I have that, I'm going to throw an exception. Our second method prints the value of a number in base B to an int. So this is going to print the value as an int. That's why I was trying to remember why we're returning void here. But it said print, so presumably print to the screen. But I'm basically going to take the string and convert it to an integer by assuming that string is representative in some of a numeric string in some base. So, I mean, you can consider 1, 2, 3 as in base 10, right? Because that's what you would normally think of if you saw 1, 2, 3. But what if that's in base 4? What if that's in base 5? What is it if that's a common thing for computers, right? What if you're in base 16? I may have a number that looks like A0, and again, I'm very sloppy with the mouse, I apologize, B1, 4, right? That's a hexadecimal number. It's a valid number because my digits can be anywhere from 0 to F in hexadecimal. So, in essence, these two parameters are tied to each other because the validity of this parameter depends on what this base is, right? If I gave you this string, but the base was anything less than base 11, then I've got an error, right? It can't be represented. It doesn't go that high. Okay, but in this case, I don't have any exceptions defined either, which means what happens in the error case. So these are all the kinds of things we need to consider, and equivalence partitioning and boundary value analysis are meant to help us with that. So for example, for a palindrome, we might consider things like, well, what if this isn't a string, right? It has white space. I want to test that it does so I know that the exception is properly thrown. What if I give it a null string, right? In fact, the specification isn't quite clear. The null string, is that considered not a string and therefore I throw the exceptions? Well, I mean, probably, I would guess, because Boolean means, I can't say it's true or false. I have no value, right? But maybe I want to fix my specification and tighten it up based on that. I may have a zero length string, an empty string. Is an empty string a palindrome? Boy, I actually don't know according to the definition of a palindrome. Or maybe that would be an error condition. Maybe palindromes are only defined on at least one letter things, like A is itself a palindrome, right? Because it's the same forward or backwards. That would be a special case as well, right? The one letter case would be a special case of a palindrome. But then I might get back to something that's more typical. But even in more typical, again, only knowing the specification, not even knowing how it's computed, I can think, well, the algorithm might have different behavior or need to be tested against odd length versus even length, right? Because if I have my ABBA here, then to compute a palindrome and determine whether it's a palindrome, I need to check that this, then this, right? But if I have something that's odd, like I misspell, again, boy, I'm terrible writing with the mouse, I apologize. But if I have something like this is still a palindrome, and I'm still testing the outer case, but now the inner case is itself, right? That same letter, it's like the one letter case, which is also odd. So I probably want to check this kind of thing, evens and odds, at least something representative in even and odd. So it's not always the case that the equivalence classes define something that's contiguous, like what we saw with the square root numbers or even the Fibonacci's, right? Going back to the error case, I could check, the white space position. Is the white space in the first or last position? Is it in the middle, right? That's an error case, by the way, where I'm trying to test for this proper throwing of this exception, but I'm considering a different basis. Now I'm considering the error basis for negative testing, but I'm putting the white space in different places, okay? So again, considering different bases in our equivalence partitioning can be important. So I have a fair number of test cases here. What about down here with method 2? Well, and by the way, we also have to consider the output space. In our output space, we're mutually, well, not quite mutually exclusive if you consider the exception to be an output space, but we basically have true, false, or throws exceptions. There isn't anything else that can happen with this method. So I want to make sure that I've got something representative where I do things that are true and false as well, right? So I want to give it things that are palindromes, odd and even. That's two different cases. And I want to give it things that are palindromes that are of length 1. I want to give it things that are not palindromes. I can't do that for length 1, but for length 3 and 4, I can certainly give it things that aren't palindromes. Then I want to give it things on a different basis for where that white space is and so forth. And in fact, I want to, not only within that, I want to combine the two. And this is what I want to get to next, and this is why I have these examples. I probably really want to give it a case where I give it something like A space, I'll use that for space, A, right? Now, if you considered it truly a string, not a word, meaning you allowed the white space, then this would be a palindrome, right? However, when you don't, according to the specification, then this is not, and it should return false, or in this case, throws an exception. We want to throw that exception in that specification. The point is we don't want to return false in this case, right? And we don't want to return true either. We want to find that and throw the exception. So we have to make sure that the proper output value is given, and we have to make sure we've constructed those variations on inputs such that we're testing a case where it would be considered a palindrome and it would not be, to make sure that the order of the logic of testing this is correct, right? This would be one that if we took away that restriction would return false, right? That's kind of the point. Okay, so even on a single, a very rudimentary return type, 2 values, a seemingly well specified definition of when you would throw an exception to get a different result outcome, and a single parameter value of a string, a primitive type, very commonly used. Even then, we get into the complexity of a number of different test cases are needed. What happens when we do the second method here? Well, you might say with this on the surface, seems like it would be a lot easier, right? I have a void return value, so I don't have different, my output space is essentially empty, right? I don't have any exceptions, and I don't have a return value to check, all right? So in that case, it is easier. I should have less of these, frankly. So I would expect out of these two methods that I'll probably have less of these. However, I do have an extra parameter. I do have 2 parameters, and not only that, but as I talked about, these parameters have a relationship, right? The validity of this string depends on, and its interpretation depends on, not just its validity, but even if it's valid, how you interpret the semantics you apply to it, how you compute a result is based on what this integer value is referring to the base, right? And we didn't put any restrictions of how big the base is. In mathematics, you can have something that's base 30 if you want, and so forth. So which means, I might have a very special edge case of negative testing case in here, for example, is what if I say that the base of the number is base 300, and I'm using the ASCII character set to represent characters, meaning in the base character set of ASCII I have 256 characters, and all of a sudden I don't have enough characters known to make up each digit in a string, so I wouldn't even be able to represent that here, right? That's kind of a far out edge case for negative testing, but those are the kind of things you have to think of, because nowhere in here did it tell me what the boundary of B is. I still have negative testing cases for negative numbers and so forth. What does it mean to have a negative base and so forth? And what would its representation be in a string if it could be represented? And then what do I do in those cases where I can't compute a valid value? It doesn't say, and I don't have a language mechanism, a return value, an erroneous return code. I don't have an exception and so forth. So this one's actually harder just on thinking at it from a negative testing perspective, but also from the perspective that these 2 parameters, the semantics of them is intertwined, right? Particularly the second one really determines how you interpret the first. So therefore, you could have a lot of tests for this one, absolutely. But then, even trying to think through the different bases, it's more difficult because essentially the space for each basis, back here we're considering, kind of one thing at a time: number of minima, location of minimum, the array length. I can consider each one of those relatively independently. Here, each basis is actually, the basis here is going to be 2 dimensions, right, for 2 different parameters at a time. And so I got to deal with those combinations as a single basis. and that's a lot trickier. And so as you get out to many parameters in your methods, that's where I'm going with this. Many parameters in your methods is considered a not very good practice. If you can avoid it, it's better from a unit testing perspective. Both, we'll see it with white box, but particularly black box testing. And the reason why is, if you're going to do this kind of analysis to come up with the test cases you want to run, the dimensionality of your data as it increases, you're quickly seeing how the number of test cases rise. For you to really say, it's not about writing one unit test. It's not about writing one black box test and saying I'm done, right? I executed for the happy day case and I'm done. You really wind up writing a number of unit test methods. You might run one. You might write one method like method 2, and wind up having to write 10 different test methods and put them together in a test case in order to consider all the different possibilities if you really want to write very robust test harnesses, right? You wind up writing more code for the test cases than you do to actually compute these things, okay? And that's part of the complexity from a software engineering perspective. How do we do that? Okay, switching gears. And again, I don't have a concrete answer. I would suspect that you're going to need more tests for this, but these are going to be harder to write. Your mileage may vary. I want to switch gears and talk a little about an alternative view. I don't know how alternative, but a different view that Agile put on this, since we're doing a lot of Agile in this class. In particular, a best practice that Agiles talk about is what's called test-driven development, or sometimes called red-green refactor. Test-driven development, what is it about? Go and look at the specification and write the test first, is what it says. Go write those 4 tests for the Fibonacci sequence first, all right? And obviously, if you haven't actually implemented anything yet, the test is going to fail. You don't have you want to test the output of something, but all you would have is stub code at the beginning, right? So I might write. Let's see. Let me see if I can switch out to my test case. So I'm going to try and write better with the digitizer here. I might have my public, I'll consider ints fib int x, right? That's my method signature. I'm not going to worry about throwing exceptions or anything else. And I'm going to compute that Fibonacci sequence number. And so to do that, I might have to write 3 test methods. One to test I had 4 here, that's right. One to test fib0, one to test, second one be test fib1, third one might be test fib5, and the fourth one might be test fib11 is what we were using, right? So I'll go write the code for those tests, and I'll run them in my test harness tool. For us, it'll be JUnit, but no matter what it is, we'll run our test for it. And those tests are going to fail because, all I have so far is this method that doesn't return anything, which means basically what I'm saying is I'd write stub code. I'd say return -1 or something. Something to just make sure I syntactically compile and can run. But I know it works. So I have the stub code there. The test cases invoke the method. They get the wrong results. I get red in each case. It's kind of purplish, but kind of red in each case. So I have all these 4 failure test cases. So I may start with the first one. And I want to make it so that one works. Right? So I may have to write the code that says if x equals 0, return 0, right, for that special case. I write that code and put it in here, and now this one passes. All right, so now I'm green, right? So what would I do again? So I added a test, I ran the test failed, I made a little change, took care of that case, and now I have to go run another test, right? The test succeeds, but now I'm going to try a test case of fib1. I'm supposed to get output of fib1 is supposed to be 1. Fib1 of 1 equals 1. So again, I'm supposed to add the two previous values. But in the Fibonacci definition, by the way, the inductive definition is the Fibonacci of some number is equal to the fib of the previous two numbers, n minus 1 plus fib of n minus 2. That's why you often see this in your, probably saw this in data structures and algorithms or something, or CST316, your second programming class when you did recursive programming. Very common thing, that and factorials, right? So now for me to write the code for, fib1 is still a special case. I don't have a 1 minus 2 case. There is no Fibonacci sequence for negative numbers. So now I have to extend this code with the else case, right? Else if x equals 1, return 1. Okay, I write that code. Now I run. The tests are green. Green means that the test passed. Now I'm going to write my next test. My next test says, let's do fib of 5. Well, fib of 5 would have to execute code that said it's equal to else return basically this equation in here, right? And that's my general recursive case. Okay, that should initially fail because all I had before this were two test cases, and when I did fib of 5, well, what was I returning? I was still returning minus 1. All right, so I was wrong, so I had to fix that by plugging in the general formula. Now I'm correct. And then I want to test my edge case. Okay, my edge case might actually work, so that one might be green to start with. But the point in test-driven development is I'm going to write, and I'm not showing the code for, but what I'm going to do is I'm going to write the code, the test case for the code first. And I'm going to make it fail. And then I'm going to go back and continually revise my actual code to make each subsequent test pass. And it's as fast. I mean, it's supposed to be test a little, code a little. It's supposed to be a couple lines at a time. So it is not unusual. Fibonacci is not a bad example from the perspective of all it took was 1 or 2 lines of code, and boom, the test will pass again. I can go on to the next test. Okay. Very often you can derive these things from your user story acceptance tests. Called red-green refactor in part because you'll see when in our unit tests that the JUnit tool will return red or color your tests red when they fail, and then when you pass they'll be green, and you'll see that in the lab. Okay. Another perspective, changing gears again, now thinking of it, so far, with the examples I've been using, these homework examples, Fibonacci, square roots, method 1, method 2, these are all functional. A lot of times we think of the unit test as the functional level. However, we can also consider a unit to be an object, right? What if our level of granularity is a little bit higher, and we consider an entire object, right? And the reason why that's important, by the way, is we typically one aspect of decomposition is functional decomposition, decomposing a large functional problem, meaning something you do, into its little steps, right? That's how you derive an algorithm, and you do that in this decomposition tree-like fashion. Any task you want to do, I want to make a hamburger for myself. Typical problem. I think Richard does that in CS1. I want to go make a hamburger. When I make that hamburger, what are the steps I need to do for that? Okay, well, the first thing I need to do is to prepare the cooking environment. Then I need to make the hamburger. Then I need to put the condiments out. And then I need to eat the thing. Whatever. I'm functionally decomposing something. A different aspect of decomposition, though, there are other ways of doing it. I can decompose problems from an object-oriented perspective, meaning identifying those things and their interesting behaviors in an environment, and then trying to figure out different ways that those things talk to each other, or what are their interactions. Hang on. Got to remember to turn on my pen. So I'm focusing on interactions between objects. So I could write a unit test per an individual method on an object, but realize it's definitely possible, and you will do that. But from an object-oriented perspective, this is still considered somewhat functional because the output of a method, a non-static method on an object, depends on the state of the object. Which means when you're designing your unit tests, your black box unit tests for a method, not only do you have to consider the method signature, our input parameters, our return value, our exceptions if they're there, but there's another thing we have to consider. We actually have to consider the state of the object, because if it's non-static, I should be accessing a class member variable, which means I have to consider that dimension of the class member variable at any given point in time when writing the unit test per method. So that can be a little bit trickier and kind of gets us into something I'll talk about in a minute with behaviors. So a lot of times what we think of is the functional equivalent of using a set of objects. And what I mean by that is usually what happens is a set of objects are called in some succession or they call each other. They have a conversation. They exchange messages between each other. When you did sequence diagrams, this is what you were representing, those interactions, those interesting conversations between objects. And so you take a functional requirement represented as a scenario, say from a use case, and you analyze and get a set of messages passed back and forth between a set of objects. That conversation is meant to be bounded as a start, as a finish. And so you can look at that sequence diagram, sometimes activity diagram or collaboration diagram. You can look at that and define a unit test for your use case by identifying those start and end points and what the functional inputs and outputs are. All right, what is supposed to be the result of that conversation? If you're doing it from a use case perspective, well, then the output's supposed to be the goal of the use case, in the success case, the happy day case of your use case. If it's something else, then you should have alternative scenarios defined or variations on your use case that might define situations where the goal is not met or the goal is met via some other alternative scenario. Okay, so these tests are often way more involved. They actually get into a much higher level of granularity than an individual method is the point. You read your textbook in Chapter 8. Somerville actually spent some time talking about interface testing. Interface testing means looking at a class perspective or at a component. If you remember your component diagrams in UML or your class diagrams, and basically looking at the public interfaces, the things that other things call, and testing those methods so that they return the proper outputs based on the inputs that you might expect. Okay, so that is an interface testing one. To me, that's not. I don't know that I consider that unit testing, frankly. I consider that a form of interface or integration testing, meaning you're now assembling different things together, classes, components, or whatnot. So what you're really doing is testing the integration of two different things. And it's usually at a relatively coarse-grained level. But that's approach one. Focus on the interactions. Yes, you can do per method. If you do it, be careful to consider object state or consider a scenario. The second approach is to consider the object itself as units. So, right, this scenario, what I'm saying is I'm going to have multiple objects talking to each other and sending messages back and forth. In object-oriented parlance, sending a message back and forth usually just means invoking a public method. All right, you can other ways of doing it, but for our sakes, invoking a public method is what I'll talk about or consider when I say messages here, for simplicity's sake. But these are distinct types. Right? This could be a class square, this could be a class rectangle, this could be a class circle, whatever. All right. If you want to focus though on an individual object, all right, and do its specification, then you need to focus on its behaviors, which means you have to have an understanding of its state chart. If you remember your state charts from UML, you have to know the set of valid states that an object can be in and how it transitions between those valid states. You may even have invalid states defined and how you can transition to those. a state of an object is defined by the values of its class members. The values that its class members member variables are defined at any given point in time. Based on the value of those variables, you may produce different computation. You may not even allow certain operations. We'll talk about that later in the semester when we talk about the state pattern. So if you want to unit test and do it at a pure object level, from an object-oriented perspective, you'd go back to your state chart. You would say, what are the things, what are the range of values of my class member variables? Now, what are the set of things, what are the set of events, what are the set of things that could happen to the object at any given point in time? That's defined by the signature of the public methods or by any events that it's listening to in the system. And so you have to try each one of those in each state in order to be exhaustive. All right. You can apply a similar kind of logic of boundary value analysis and equivalence partitioning, but you would be doing that with an extra dimension to it, considering the state of the object at any given point in time and all the states across the state chart of the object. So again, kind of exhaustive unit testing for an object can get quite involved when you're looking at it from the object perspective and not from just the individual method perspective. All right. And then finally, you see we have, I was trying to compare a little bit. This, by the way, starts to get into white box testing because you'll really want to be kind of tracing the code of your object at that point, and I'll get to that with the next session. We got our black box, we got our white box. So why is there a gray box over here? Gray box is kind of an emerging concept where our testers may be more informed. They may be programmers themselves. They may be told things about the code, about how it computes things, and so they can use knowledge of those internal structures without necessarily having the code itself. So maybe they're given documentation on how something is done. And they use that knowledge to construct more detailed test cases, trying to explore and get to the nature of some causality of our tests. And this is particularly used in security when you're doing something called pen testing or penetration testing. A security-oriented penetration tester needs to know something about how the system works in order to devise more detailed and better penetration tests to make sure it's really exploring the different set of cases that it can do. Now, without the code, it may not be as good as white box testing. You still have limited visibility, but through documentation, through an understanding of how the system works, can try and devise ingenious ways, hacking ways, in order to expose potential security flaws in the system. So that's why I mentioned gray box testing here, often used in our security-based pen testing. Okay. Finally, in wrapping up, who actually writes the unit tests? This is basically the thing is here. Do you as a developer write your own unit tests, or does somebody else? Right? If you write the tests, there's some benefits of that. One is, you're taking responsibility of the code. You're making sure it's been tested in some reasonably rigorous way by yourself at your desktop, if you will, before you give it out to other developers. All right. Some benefits of that: the code best as a developer. But so how to test it better. One of the drawbacks is the code best, right? Which means you may have some bias. You may get a little bit lazy about considering the full range of black box tests to write. You may have some blind spots. I mean, if you already thought of how to design it and how it should work, then you may not have an intuition about how to vary your testing in order to make sure you're doing things like negative tests where the code would bomb or where you would get different results. All right, you may have the blinders on because sometimes when we see a solution to something in our mind, in our intuition, sometimes it can be hard to get away from that and take a different perspective. And very often you may need a different set of eyeballs to look at the same problem a different way, and therefore come up with a greater spread of test cases to ensure more robust code. Certainly, when we do test-driven development, we're assuming it's the developer. Him or herself that's doing it, because it's part of that little test at a time approach, that red-green refactor approach we talked about. Another approach, though, is to take that someone else writes the tests of the code you just produced, right? And this is the other direction, right? You have that other set of eyeballs. What I was saying, the benefit is, somebody who doesn't know the code already is not going to have that same bias, is not going to have that lock-in intuition on the design. So there's some benefit. If it's a developer, if it's another peer developer, it may create some familiarity with the system. This says with the code, that'll happen with white box testing. With black box testing, not supposed to be about the code, but we'll get some familiarity with the functionality of the system. The drawback, that person doesn't know the code already, all right? Which means if they're trying to devise a black box test, and again, same kind of problems we'll talk about at the end of white box testing. If they don't know, it's going to take longer to develop those tests. They got to understand what it's supposed to do, the specification. They got to look at the functional specification, and then on top of that, it doesn't support test-driven development. In general, it's going to take longer too, right? So a lot of unit testing at the lowest levels is very often done by the developer, him or herself. Very often, unit tests are subjects of code reviews, meaning it's not just about reviewing the code that does something. It's all about it's also reviewing what the developer wrote as unit tests as part of that red-green refactor process, so that the other developers are reasonably confident that a good set of unit tests has been written. All right. Open question. I mean, I want you for your acceptance test for user stories to have another set of eyeballs on it, but that's not the same thing as a developer writing the unit test for that quality practice. For that, you're largely going to write your own unit tests. However, those things should be reviewed within your team. What did you actually write for a unit test, and did you consider a good range from a black box perspective? All right. Our next perspective is going to be consider the white box one. We'll revisit some of these same concepts like we just talked about, who writes the test and so forth. The point of white box is now you have the code, and you want to make sure the code is exercised in all different sorts of ways, so that you know each individual line of code. I mean, one way to think of white box is calling the unit an individual line of code and going all the way down to the individual lines of code to test them for correctness. So it's a bit more involved, a bit more detailed, and that'll be the subject of our next talk.